Hey, BC Calculus, it is Mr. Canfield. Today we're looking at polar coordinates, and specifically we're going to be doing derivatives with polar functions. So this is going to be part 2. I never filmed part 1. Hopefully part 1 exists for you in the future. For my future students who I don't have yet. Okay, all right, so, sorry, okay. I have filmed this twice. This is the third time. Let's see if it goes right this time. Okay, so R is equal to theta junk, right? So if we were going to take the derivative of this, it would be dr d theta. And so like we could totally find that, and that's a thing. So that's great. But it's going to be dr d theta is equal to more stuff in terms of theta. It's not going to tell us the slope of the line. It's going to tell us the change in rate per the change in the angle. If we want dy dx, what we're going to have to do is we're going to have to use those formulas that we know, such as x is equal to r cosine theta and y is equal to r sine theta. If we use these, then we can take the derivative of these. We're going to wind up getting a dx d theta over here and a dy d theta over here. And just like with parametrics, now I can take this one divided by this one, right? dy divided by dx. We're going to get dy dx doing that. So, and then we're going to have to talk about horizontal and vertical tangent lines. So, let's go. 2 sine theta. R is equal to 2 sine theta. And we're restricted here between 0 and pi. So that's going to be important later. So if I want to find, the actual question asks for the horizontal and vertical tangent lines, but I want to talk about how we find dy dx, because that's an important thing for us to know how to do. So, well, I know that x is r cosine theta, and we know what r is. R is this thing. So I can say x is equal to 2 sine theta cosine theta. And that looks like a 0. Okay. If I want to find dx d theta, well, I just have to take the derivative of that. I just have to be careful. It's 2 sine times cosine, so I got to do product rule. So I like to take the first derivative first and then the second derivative second. You can do whichever way you want, but if I do that, I get 2, that turns into cosine, so it's cosine cosine. And then this turns into negative sine. So it's minus 2 sine sine, or 2 sine squared. So that's our dx d theta. So our dy d theta, very similarly, r sine theta, dy d theta, back up, Canfield. All right. So r is 2 sine, it's 2 sine times sine, so it's 2 sine squared theta. So our dy dx then, the 2 is going to come out front, we get a 4. I almost wrote cosine, keep the inside the same, then multiply by the derivative of the inside. So that's going to be our dy d theta. I've had people ask me, do I have to do chain rule? Can I write this as 2 sine sine and do product rule? Yes, you can. The thing about these rules is they are consistent. It doesn't matter which rule you apply. If it's allowed to be applied, you can apply it. You can do it. Like you can even do product rule where you take the derivative of the 2 as you do this. The thing is the derivative of 2 is 0. So you would have 3 different terms and your first term would be 0. So it'd be 0 plus that minus that. So there's a lot of internal consistency with these things. As long as you do something that's legal, it'll work, even if it's not the most efficient way to do it. Okay, so if I take dy divided by dx, that's going to give me, I should at least show this once in the video. The thing is, this divided by this, we keep change flip. So I took this, flipped it upside down. The d thetas cancel. It gives us dy dx. And so I just put dy on the top, 4 sine theta cosine theta, put dx on the bottom. And there we go. This would be dy dx. So if I want to know the slope at any point on this curve, and this curve happens to be a circle, it's a circle that's offset, I believe it's something along the lines of this. If I want to know the slope at any given point, all I need to do is find out what angle, what theta we plugged in to get to that point, and that's going to tell us the slope. So we're looking for slopes that are 0, which is going to be here and here, and we're looking for slopes that are vertical or undefined. So it's pretty simple if you remember how fractions work. You get 0 when you have 0 divided by a number, and as long as this number is not 0. Because 0 divided by 0 was a weird issue, and we spent a lot of time with limits, finding out what happens when you get 0 over 0. So 0 over number, as long as it's not 0. Okay. Well then, that's going to be horizontal tangents, HT. I just got to take the numerator of this fraction, 4 sine theta cosine theta, set that equal to 0, and solve it. That's literally all you have to do for something like this. This is 4 times sine times cosine. 3 things multiplied together equals 0. Basic algebra tells us that 3 things multiplied together equaling 0. If any of them is 0, the whole thing is 0. Is 4 ever 0? No. What about sine? Is sine ever 0? Yeah. Sine of theta is equal to 0 when theta is equal to 0 and pi. What about cosine? We get pi over 2. You also get 3 pi over 2. And this is just, between 0 and 2 pi on the unit circle. But if you remember, in this question, we actually only care about from 0 to pi. So, fine. Wait, are these fine? Yeah, it's allowed to equal the endpoints. If it wasn't allowed to equal the endpoints, neither of those would be fine. Pi over 2 is good, but 3 pi over 2 is excluded. Okay, these are all potentially horizontal tangents. What I need to check for, though, is, are any of these a 0 in the denominator? Because if they are, then they're not horizontal tangents and they're not vertical tangents necessarily. We don't have enough information to understand what's going on. So 0 divided by a number, that was equal to 0. What's a number divided by 0 as long as this is not 0? Undefined. So this is undefined. So all I gotta do is find out, hey, when is this equal to 0? I'm gonna show you my way, and then I'm gonna show you Stu's way. I don't like my way now that I know how Stu did it, but I want to give you a variety of ways to approach things algebraically. First thing I'm gonna do though is divide everything by 2. So divide this side by 2, divide that side by 2. No reason to not do that. It has no effect on the answer. 0 divided by 2 goes away. So I looked at this and I said, oh, well, I can do cosine theta plus sine theta times cosine theta minus sine theta. I just factored. It's the difference of 2 squares. And then if I solve this one, I get cosine plus sine needs to equal 0. I can subtract the sine from both sides. Okay, when is cosine equal to negative sine? Well, they're only ever like the same number at the pi over 4s. So where would a pi over 4 be where they have opposite signs? Well, it's going to be like up here and up here, right? Because this is minus plus and this is plus minus. And this is the only, we're going up to pi, right? So I don't care about down here, so I can say theta is equal to, that's pi over 4, that's 3 pi over 4. And then on this one, it's cosine theta minus sine theta is equal to 0. Add the sine to both sides. Now it says cosine and sine are equal to each other. So that's going to be when their signs match. You had regular pi over 4 and at 5 pi over 4 over here. So again, since we only care up to pi, say cosine, or we can say theta is pi over 4. So here are 2 vertical tangents. I forgot to write that. those are our two vertical tangents, or potential vertical tangents. And then I look over here, yeah, there's nothing in common. So these are vertical tangents, these are horizontal tangents. Boom, there we go. And it says verify graphically if we go in and reset the calculator. Let me go into polar mode. I'm just resetting because I want to start fresh every time, just in case you start with a fresh calculator. Remember, we are in radian mode in this class, essentially every time. There's almost never a time when we're in degree mode in this class. That's the default for this calculator, but if you take physics, you likely are using degrees in there, so be careful just to switch back and forth. Okay, let's see. 2 sine theta. If I look at this, let me zoom fit. So it says I've got 3 horizontal tangents. Well, let's see. If I click trace and type 0 for theta, that's right down here at the bottom. Yep, that's a horizontal tangent. What about pi over 2? That's my next one. Yep, that's the very top. And then you might be able to figure it out. At pi, we're back down here to the bottom. If I look at pi over 4, sure enough, over here at 1, 1. So we can assume 3 pi over 4 is going to be this negative 1, 1. Let's see. Yep, right there. So there, I did some verification graphically for myself. All right. So now for the problem that I can't seem to do correctly, mainly because I changed a negative sign to a positive sign. It's not that this problem is super difficult to do. It's that typos are a thing. And typos are very hard to catch. So when it's just you in your own little individual echo chamber. Okay, so how are we going to find the horizontal and vertical tangents to this? Well, we don't actually need to find dy dx. We just need to find dy and dx kind of separately. So I know that if I want to find my vertical tangents, that has to do with x, because x is on the bottom of that fraction. So x is going to be r, right? This is r times cosine theta. And it's really up to you. Do you want to leave it like this and then take the derivative, or do you want to multiply it all out and take the derivative? It doesn't increase or decrease the difficulty of it. It's whatever your organizational preference is. So I'm going to distribute the 2, and then I still have to multiply by cosine theta. So 2 cosine theta minus 2 cosine theta sine theta. I am more comfortable looking at it like this personally. I can take the derivative of this over here. And if you are going to do that, I'll write what I would get for that in just a minute. So dx d theta, I get negative 2 sine theta. My voice is getting gravelly. This is fun. Then I got to do product rule here, and I got a minus 2. So one way to handle that is to write minus 2 and then just do the product rule in there and then distribute the negative 2. That's probably the safer way. And since I've made so many mistakes trying this problem in the past, I'm going to be more careful. So let's see, derivative of cosine is negative sine, so I get negative sine squared. And then I'm going to get plus cosine squared. Okay. And then I'm going to distribute the negative 2 here, and I get negative 2 sine theta plus 2 sine squared theta minus 2 cosine squared theta. Okay? Okay. Okay, okay, okay. And then if you did this way, I would get 2 times negative cosine theta. Oh. Well, that's fine. Minus 2, 1 minus sine theta sine theta. So I get negative 2 cosine squared theta minus 2 sine theta plus 2 sine theta squared, sine squared theta. It's the same thing. Okay, so pick this one, pick this one. Oh wait, they're the same, right? And I'm setting this equal to 0 and trying to solve it. So if I'm doing that, well, they've got a bunch of 2's, right? So I'm gonna divide both sides by 2. That's a, like, pro tip, makes life easier. So here's the trigonometric trick that we use to solve a problem like this. This is very, very close to looking like something like negative x plus x squared. If only this was something with x stuff instead of saying what it currently. So right now this says cosine stuff. If it was sine, sine, and sine, there'd be like factoring or something that we could do to solve this. So enter Pythagoras. Remember sine squared? That's a squared. Sine squared plus cosine squared is equal to 1. So I can actually solve this for cosine squared. I can subtract the sine squared and say cosine squared theta is equal to 1 minus sine squared theta. All right. So I can say 0 is equal to negative sine theta plus sine squared theta minus 1 minus sine squared theta. So, and like I want to completely like make sure that I am throwing myself under the bus here. I didn't just make a distribution problem. Like, I did this fine. I just dropped the negative on that between 2 steps. It completely changes the answer. All right, let's see. I got 2 sine squared theta minus sine theta minus 1.
Okay, I didn't do anything wrong. Stu does have a typo here, but the rest of his work is correct. Okay, all right. All is not lost. I mean, even if that was wrong, all would not be lost. Okay.
We can factor it now, right? This is 2x squared minus x minus 1. So if I was factoring that with x's, I know I would need a 2x and an x to make this FOIL back out, and I would need a 1 and a 1 to make this FOIL back out, and I just have to figure out, since it's a negative 1 at the end, which one of these is plus and which one of these is minus. So if I reverse FOIL and just kind of think about it, I wind up getting that. So the situation here, also, if that's a difficult thing for you, there's a bunch of tricks, there's a bunch of ways to do this. I can show you a way. Don't mind helping. All right. So instead of x's, we're using sine theta. And now solving this is pretty straightforward. We just go, okay, so 2 sine theta plus 1 is equal to 0, and sine theta minus 1 is equal to 0. So I'll subtract the 1 divided by 2. I get sine theta is equal to negative 1/2. And then sine theta is equal to 1. So sine is equal to 1 at the top at pi over 2. Now we're going to figure out this one. And we're going to do, you can do the unit circle and know your answers immediately. I know where they are, I know what they are, and so I know my answer. But let's just, let's say you forget your unit circle. It says sine theta is equal to negative 1/2. Well, I know that sine is opposite over hypotenuse, so like this would be negative 1/2, but I can't go up negative 1, so you know it's not there. I know it's got to be down here. Similarly, I could go this way. And so these are going to be my 2 possible triangles. I just have to figure out what that central angle is going to be. Oh wait, it's across the street from the 1, so they're 30 degrees, right? So I come down this way 30 degrees, and 30 degrees is pi over 6. So I could say I'm at 12 pi over 6. I'm going down 1. So that's 11 pi over 6. And then this one, I'm at pi and I come down 1. So that's 5. No, wait, this is 6 pi over 6, right? So then it'll be 7 pi over 6. So that's the way to do this without unit circle memorization of coordinates and stuff. So so these three are all potentially vertical tangents. And you can go through and do the exact same thing for y to get your horizontal tangents. And we're going to see something interesting with this problem if I remember correctly. So let's see. Y is equal to r sine theta. So I'll just distribute everything out like I did before. So 2 sine theta minus 2 sine squared theta. So then dy d theta is going to be 2 cosine theta minus 2 sine theta cosine theta. And that's equal to 0. Divide everything by 2. So now I can, that's a 2. Why, that's not a 2. The 2, I divided it by 2. Oh, boy. All right. There, I didn't do it. It's just an S. It's just, that's an, okay, so I'm going to divide a cosine, not divide, factor a cosine out. Real quick, why did I divide both sides by 2, but not divide both sides by cosine? Let's talk about that really quick. Dividing both sides by 2, 2's not an answer. Like 2 doesn't have an x or a theta in it. There's no way that 2 affects our answer. It's a scalar essentially. If I were to divide both sides by cosine of theta contains one of our answers. And so if I'm dividing both sides by something that contains one of our answers and it disappears, I'm losing an answer. So when does cosine theta equal 0? Oh, it happens to equal 0 at pi over 2. Oh, so we got pi over 2 both times. That's a problem. So we'll talk about what happens there when we look at the giraffe. 1 minus sine theta, let's set that equal to 0. So I'll add the sine to both sides. 1 is sine equal to 1 at pi.
Wait, what did I do? I'm doing something wrong. I'm doing something dopey wrong. Oh, be careful, Canfield, be careful. Hold on. Oh, goodness gracious.
Harumph. This is a 4. This is a 2. So, after all that, there should have been a 2 there, even though, oh my goodness, I'm sorry I had to see that. I don't have a ton of time right now. I gotta leave this in. Bloopers. Okay. 1 is equal to 2 sine, so 1/2 is equal to sine theta. Okay. Good old bloopers. So that makes sine theta, let's see, that'd be here and here, right? Where we'd have a 1 over 2, or 1 over 2. So we got 30, which is our pi over 6. And then we've got, if this is 6 pi over 6, it's the one before it, so 5 pi over 6. So that leaves us with voidical tangents at 7 pi over 6 and 11 pi over 6 and pi over 2. And then horizontal tangents at pi over 2, 5 pi over 6, and pi over 6. All right. Oh, wait, I forgot one. I forgot one for both of these, didn't I? I forgot that cosine's also 0 at 3 pi over 2. So I actually have another answer here. So now we look for any overlap. And we say no, no. Okay, and we're done. If we go look at the graph, let me zoom back to standard. 2 times 1 minus sine theta, hit graph. So my y values, let me go from -1 to -1 to 1, or maybe -2 to 2. Boing, 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 wow. Okay. You'll see that there's a strange, wait, why don't I just hit zoom fit? That usually takes, yeah, there we go. There's a weird point there. We have a cusp there, and that cusp winds up happening at pi/2. So we got a little bit more to look at, but I hope this was helpful.